Okay, video 2 for section 3.4. This one will go very quickly. Last time we learned about how to actually find a horizontal asymptote, doing it algebraically and using the limit and everything. You're still going to want to try and figure these things out using probably the old method. So we're going to look at growth rates, and you should be able to look at most of these and be able to determine them very, very quickly. So there's only a couple things in here that we're going to look at that have a little bit of difference to them. In this case, let's look at number 2. We want to find the limit as x approaches infinity of x squared minus 9 over 2x minus 4. It should be very obvious that the growth rate on the numerator is greater than the growth rate in the denominator. And when that happens, the limit goes to infinity. So that's it. Nothing else that we need to do there. And you want to be efficient with this stuff. You don't want to have to think about it. You don't want to have to do all the extra algebra and stuff unless it's requested of you to do. Number 3. The limit as x approaches negative infinity of 2x squared over 3x squared plus 1. Again, looking at the growth rates, the growth rates on the numerator and denominator, again, you're looking at the greatest growth rate. Okay, we're not looking at anything less than that, so we're ignoring the plus 1 for the most part here. The growth rates are the same. So we know that you just divide the leading coefficients, and you're going to get 2/3. That's it. That's your limit as x approaches negative infinity. So the only question you might ask yourself is, well, wait a minute, it says it's going to negative infinity. Well, yes, but if you plug large negative numbers into the numerator and denominator and square them both, it's going to be positive over a positive. So you're going to get 2/3 out of it. Number 4. I'm looking at the numerator and thinking, okay, there's no variable in there at all. So the power in the denominator is definitely going to be greater. So the growth rate in the denominator is greater than the numerator. And if that's the case, always goes to 0. And that's it. I mean, these, again, should be really easy to do. You just have to think about them. Okay? Now, we do have to think about this one just a little bit more. Limit as x approaches infinity of cosine of x over x. Well, now we're not just dealing with polynomials anymore. Now we've added trig functions in there. This is where you really need to understand your functions. Cosine of x is bounded. It cannot be bigger than 1. It cannot be less than -1. So no matter how big no matter how big x gets towards infinity, cosine at most can be +1. It will technically keep bouncing back and forth between positive and -1. So the numerator is going to stay relatively small while the denominator grows very, very, very large as x goes to infinity. So the growth rate in the denominator is way bigger than the growth rate in the numerator, which means this goes to 0. Okay, similar concept on number 6. As x goes to infinity, again, the numerator is 1, so it's not going to grow at all. The 2x in the denominator is actually your dominant growth rate, because again, sine is only going to bounce back and forth between positive and -1. As x gets really large, the 2x part will grow very, very, very fast compared to the numerator. So this one is also going to approach 0. Again, a very large denominator, very small numerator. Okay, limit as x approaches infinity of sine of 1 over x. Not to be confused with the limit as x approaches 0 of sine of 1 over x, which had no limit because it was oscillating. This is what happens as x gets extremely large towards infinity. Well, as x gets very, very large towards infinity, this part, or the angle part, is going to approach 0. So then you can ask yourself, well, if the angle approaches 0, sine of 0 is 0. And that's it. That's what you're looking for. All right. Now let's go on to a couple that are actually slightly more interesting. Number 8's not really one of those. Number 8's going to be just fine. Again, look at the growth rate of the numerator and denominator. The cosine part, again, we know that bounces back and forth between plus and -1. So it's really the x's that are going to be the dominant terms on the numerator and the denominator. So if that's the case, and these are the dominant terms, you're looking for the leading coefficients here, which is 1 over 1. So the limit is 1. Again, really is not very difficult to see most of these. Number 9 and 10 are going to involve just a little bit more here. And I wish I had given a slightly different example for number 10, but we'll still show it, and then I'll hopefully explain that it's not always going to work out the way it does in number 10. All right, in number 9, you have to look at the growth rates again, but you have to be careful here. Remember that you're kind of ignoring, it's not that these aren't part of the function, but the growth rates of the highest powers, or the growth rates of the dominant term in the numerator and denominator, is really all we're focusing on. So we're not really worrying about those. We're not really crossing them out. I'm just doing that to show you that that's not really what we're looking at as far as the limits as x goes to an infinity. The dominant term on the top is 2x. The dominant term on the bottom looks like it might be x squared, but don't forget that square root's there. So it's really like the square root of x squared, which is basically like saying x. So the dominant term on the top is a 2x. The dominant term on the bottom is an x. Here's where sign analysis comes into play on this one, though. If I were to plug extremely large negative numbers into the numerator, I'm going to get a negative value on top. If I plug those exact same large negative numbers into the denominator, well, I have to square them first, and then you have to take the square root. So when you square the large negative numbers, you're going to get a positive. Then you're going to take the square root, which we know has to produce a positive anyway. So you're going to get a negative over a positive, which means since these two things basically have the same growth rate, and you have to take the leading coefficients, what you're really going to get here is 2 over 1, because those are the leading coefficients, but it's a negative over a positive, which creates a negative value. So really, the limit here is -2. And you have to be careful. Just because this thing is approaching negative infinity does not always mean that your answer is going to be negative. As we saw before, we had one that approached negative infinity, and it was a positive value. You have to evaluate and use some sense, some number sense, as far as what the sign is going to be. All right, and the last one. This one's an interesting one because if you look at number 10, and I'm going to plug in really large negative numbers into both of the x's, it looks like that square root of x squared plus 1 would go off to infinity. We know x would go off to infinity. It'd be really nice if we could always say that infinity minus infinity is 0, but remember, infinity is not a number. It's a concept. So we actually have to do a little bit of math here. You could also, by the way, get some other form of infinity because things go to infinity at different rates. Or we could actually end up with an actual finite value. So let's go ahead, or a finite value other than 0. So let's go ahead and see how we would do this. Because you can't just say infinity minus infinity. Oh, that's 0. Oh, it's infinity. We don't know that. So what we have to do is we have to create a fraction out of this. Whoops. Let's try and make an actual fraction bar. And we're going to use the method of the conjugate here. So I'm going to multiply the numerator by x squared plus 1 plus x, and the denominator by the same thing. And then we're going to simplify our limit and see what we can get. So we get the limit as x approaches infinity. Okay, multiplying the numerator, we're going to get x squared plus 1. The outside and the inside, if we FOIL those, are going to go away, so then we get minus x squared. And then over the denominator. And then if we simplify this one more time, looks like the x squareds in the numerator will subtract out, so I get 1 over square root of x squared plus 1 plus x. And now it's pretty clear to see that the numerator does not change. The denominator is going to grow very large. This one will approach 0. So in this case, the infinities actually did subtract to 0. Doesn't always happen. Sometimes you actually get a finite value other than 0, and sometimes you might actually get infinity. Just depends on how it all works out mathematically. Okay, that is plenty enough. I hope that this will turn out to be a relatively easy assignment.